Marine in Cape Town, South Africa. And we are a naval architecture company, and we specialize in the design of hydrofoil supported catamarans. And my presentation today is specifically on our experience on designing these vessels and touching on some of the research aspects as well. Okay, so an overview of my presentation. I'll start with a short introduction. I will discuss some of the history of these type of vessels. I will also show some of the more significant vessels which have been built over the years. Discuss the main advantages, some design considerations, and then I will finish off with what we are doing at the moment, specifically in relation to Russia. So just quickly as an introduction, a hydrofoil supported catamaran is a catamaran hull with some kind of hydrofoil or wing system between or under the hulls of the catamaran. There are very many different configurations. The Hyzercat system is the one which was developed in South Africa and which we normally use. It is a main foil between the hulls with two smaller wings at the stern, very much like conventional aircraft. The tandem foil, where you have two foils roughly the same size, is also quite commonly used. And the simplest system is, of course, a monofoil. And what I've also used, what we've developed in South Africa is this, what we call the Hyzercat system, with a very high aspect ratio foil near the bow and a large foil near the stern. I know in Russia, this system has been developed with canards, with interceptors, and there are other variants too, but these are the ones which have generally gained acceptance in the world. Okay, this is a very busy slide, but I try to put the whole history of this development into one slide. So I'll just run you through it. Basically, hydrofoil supported catamaran development, the first serious research into this work or this type of vessel was done by engineer Yermolayev in 1972. I think he worked at the Krylov Institute. Unfortunately, as far as I know, no vessels were built of this type. And the first vessel I know of was a large 40-meter catamaran built for the US Navy. It was a displacement ship where they added hydrofoils to improve the seakeeping, and that was reasonably successful. For high-speed hydrofoil supported catamarans, my university, Stellenbosch University, started this development in around 1980, with the first prototype being built then. And this has by far been the most successful design variant. And even 40 years later, we're still designing the vessels very much along the same principles. And there have been thousands of vessels built of this Hyzercat configuration. They range from 6 meters up to 36 meters, and the fastest ones are about 70 knots. In the 1990s, there was really a very big development around high-speed passenger vessels, catamaran ferries with hydrofoils. Japan, Hitachi and Mitsubishi developed their own variants. Norway had their own foil cat development. The Koreans, Daewoo and Hyundai, also spent a lot of money developing hydrofoil supported catamarans, but only one vessel was built by Daewoo. And company MTD in Russia also started their development of using canard hydrofoils with interceptors, and the first vessel was built in 1998 in Singapore. Australia started to develop the same ideas using trimaran hulls. And in South Africa, we developed this Hyzercat system, and sort of eventually 3 vessels were built of that type. United States also tried some developments, built some experimental craft, but nothing went into commercial use. And more recently now we have some interesting developments from the UK where they're using catamarans with different sized hulls. So it's essentially a monohull with an outrigger and hydrofoils from a company called BAR Technologies in the UK. And we are working quite closely with CTech in Russia, developing the Alpha series of new hydrofoil supported catamarans. Okay, this typically the Hyzercat, as I mentioned, is a main foil with 2 stern foils. And in its optimum configuration, it uses a asymmetrical catamaran planing hull. So it's ideally suited to planing catamarans. And it has many advantages. You can get up to 40% higher speed with the same engines, very good, much better load carrying capacity, better sea keeping. And the hydrofoils typically carry around 50% of the vessel weight. This is a graph which sort of shows the resistance tendencies. We have fruit number on the x-axis and the resistance displacement ratio on the y-axis. And you can see a catamaran hull with and without foils. You can see from roughly fruit numbers of 2, you get a very big reduction in resistance, roughly flat resistance curve. And once you are up at this fruit numbers above 4 or 5, then the performance is competing very well with conventional hydrofoils where the hull is lifted completely out of the water. So just to give you an idea, I've got two videos here just to put some practical visualization into it. You can see typically how a Hyzercat foil system looks on a hull. This is for a 17-meter boat running approximately 30 knots. And here, 2 different videos. You can see the foil is very shallowly submerged. This is a foil at keel level, and you can see a stern hydrofoil in the water over there. Okay. Oops, let me just go past this. I'll run through a few other developments just quickly. This was what was developed by Hitachi in Japan. They used very slender hulls with very wide tunnels and hydrofoils with active ride control. Their main focus was to improve passenger comfort in rough seas, off the seas of Japan. And while they got very good seakeeping characteristics for their vessels, the resistance characteristics were not so good. Due to the hull shape. And a few vessels were built, and then this development was stopped. I think only about 5 vessels were built in total. The Norwegian development, also very much money spent on it, to using technology which was very similar to the Boeing jet foil. It was a lot of input from Boeing or old Boeing engineers. Gives you an idea, a steerable bow foil, and there's a stern foil with a very big water jet intake. And only 2 vessels of this type were built. These pictures at the bottom are of the last remaining vessel which is operating in Hong Kong. I took these pictures myself. So the superfoil, I think probably this system is quite familiar to many in the industry in St. Petersburg, as it was developed there. And using bow hydrofoils and stern interceptors. It's quite a challenging system to use and get right, because the hydrofoils at the bow are quite small. And so the boats are quite weight sensitive. This first vessel in Singapore was not so successful. It could not lift onto the foils when it was fully loaded. But the second vessel, which was built in St. Petersburg at Almaz, that was very successful. according to what I know. Okay, the Hyzercat is the other system which I've spent quite a lot of time working on. My PhD study was very much around the development of these hydrofoils, and it was developed for very large catamarans. The hydrofoils carry about 80% of the lift, and the performance which we gained, you can see, got very good resistance displacement ratios, almost improving on conventional hydrofoil boats. And this is really because of the large hydrofoil at the bow, and also positive interaction effects between front hydrofoils and rear hydrofoils. Here you can just gives you an idea of how the same boat with and without hydrofoils runs. We retrofitted this vessel with hydrofoils in Hong Kong. You can see with 40 knots without foils, 46 to 48 knot with foils, and you can see the difference in the waterline. Idea of the hydrofoils. This hydrofoil is probably the largest foil which has been built in the last 50 years anywhere in the world. It is as you can see, a 12-meter span, very big hydrofoil, carrying roughly about 250 tons of load. And so far, 3 vessels of this type have been built, and 2 in the United States and 1 in Hong Kong. This shows, I just want to show you a little bit, if I can just figure out how to speed up this video now. There we go. To show you how the hydrofoil, such a big, large hydrofoil runs. And you might ask what is happening on the foil itself. That is actually some ventilation. It's not, and high turbulence, so that you get a mixing layer on the surface of the hydrofoil, a mixture of air and water. So actually cavitation is not really possible on these type of shallowly submerged hydrofoils because of the turbulence. So if we compare the sort of the efficiency, I've used what we call EP, which is a ratio of the installed power to the speed times by the displacement. So the lower this value, the more efficient the craft is. Sometimes people use the transport factor, which is the inverse of this. But basically, if one compares the EP value versus Froude number, where EP is increasing efficiency is a lower number, semi-displacement craft such as conventional catamarans typically have this state-of-the-art curve. Hydrofoil craft typically have this kind of state-of-the-art curve. All these blue triangles are conventional hydrofoil ships. Many of these are vessels which have been developed in Russia and the Soviet Union. And all the X's are hydrofoil supported catamarans. Typically the Hyzercat system are these vessels here. So they are not as good as lifting the hull completely out of the water in some applications, but they have hydrofoils which are at keel level. Once you put the hydrofoils below the keel, you can start getting much better efficiencies. And in my opinion, from what I've seen, you can improve on a conventional hydrofoil ship. Now, the reason for that is often to do with the propulsion efficiency, is that with a hydrofoil supported catamaran, you can use conventional water jets, conventional propellers, and that gives you a better propulsion efficiency. Once the hull is completely out the water, the propulsion is quite a challenge. So in terms of the application, for Hyzercat vessels, we typically you need to have a certain minimum speed for the length of the vessel before you can apply the technology. So roughly it works out that for a 30-meter vessel should have a speed just slightly less than 30 knots, or a 25-meter vessel should have a speed slightly more than 25 knots. You know, it's roughly length and speed go together, you know, as a minimum for a Hyzercat, as a rule of thumb. For a Hyzercat system where you have foils below the keel, you can actually you can work approximately according to a volumetric fluid number of 2 is what is needed before hydrofoils become useful. Now, how we approach the design of these vessels is typically we do a simple feasibility study based on fluid numbers and transport efficiencies to establish if the boat is worth using foils on. Once we proceed, we use we've developed our own in-house mathematical models, and for Hydrofoil Theory, I have gone back to one of your great textbooks on hydrofoils from 1971. I'm sure you're all familiar with it. Hydrodynamics of High-Speed Craft by Yegorov and Sokolov. And the hydrofoil theory in there is, I think for a simple theory, it cannot really be improved upon. I've validated over many, many years. I'm still using exactly the same hydrofoil calculation methods. Works very well. I've combined that with a planing theory of Daniel Savitsky, which, if you combine the two together, that gives you a very useful design tool for normally from there, we still make use of Professor Kornev's auto wing vortex lattice method. Find it very, very useful in designing the foils, especially once you have to consider more complicated interactions or complicated foil shapes. We also make use of Rand's CFD methods for the more complicated hulls or for a final performance prediction. And for seakeeping and calculating seakeeping, we use a software package called ShipX Veres from Sintef in Norway, or used to be called Marintech. And I will touch a little bit on structural design and fabrication just now, but further in the presentation. As I said, we often use AutoWing. This is I did a lot of work with Professor Kornev and Dr. Taranov, who are really the brains behind that software package. I only did a little bit of work on it, but I find it very useful for the foil interactions. And something which is also very important is to work out the path of the tip vortexes. The tip vortices should, of course, not go into the propeller or the water jet. And so I find because the method calculates the tip roll-up process, I find that a very useful feature, which of course cannot be so easily calculated with the Reynolds average Navier-Stokes method. So the only limitations is in the software is you cannot so easily calculate the equilibrium conditions or the hull foil interactions. However, we've developed our own sort of method for calculating the equilibrium conditions, and it's been it's part of our sort of standard design tools for hydrofoil supported catamarans now. When we have complicated vessels, like for example, this hull, this is almost a semi-displacement hull, which was which we had to retrofit foils onto. Doesn't have a very good shape. It's got a bulbous bow. But the client wanted foils. So then that's usually when we revert to the RAND CFD methods to try and find a solution. And but in general, it is only useful to do a few validation points to check that you're reaching the performance. Even with this system, the foil system was designed using simple empirical methods from that textbook. So, and only a couple of validation runs to check that we got it right. Like I said, I'll just run you through what we do with ShipX. In more recent times, we found that our clients don't really just want to look at improvements in speed or fuel consumption, but the sea keeping and having a larger operational envelope for the ships is far more important. And therefore, we eventually looked at various tools, and we found this is the most practical tool for us. And it's a high-speed strip method with modules for hydrofoils built into it. And for example, here we investigated high-speed crew transfer vessels which go to the oil rigs. A hydrofoil supported catamaran with a conventional monohull. They are roughly the same sizes, same speed, a little bit different. But by comparing the two, we could work out the response amplitude operators for pitch and heave in different wave periods and wave height, and establish what is the most optimum foil system to use to get seakeeping improvements. And eventually you get to the point where you can get the operational envelope, and we can prove to our clients that yes, you have a much larger operational envelope with a hydrofoil supported catamaran than with a monohull, because the hydrofoils generally damp out the motions in waves. Even with this is for a fixed hydrofoil system. Of course, if you add ride control to it, it becomes even better. But that we find is a practical design tool. We are only in very rare occasions do we use RANS CFD methods or to calculate motions in foils. Again, it tends to be quite expensive. It is quite, also the turnaround times are very high. And unfortunately, all our projects always seem to be, the client wants the result yesterday, and we have to work extremely fast and try and get practical solutions in very short times. Now, one area of research which I feel has been very lacking, but it is a very big problem in design of hydrofoils, is the problem of striking floating debris, or in a worst case, even like hitting rocks. And with hydrofoils, the hard question which always comes up from a client is what happens when the hydrofoil hits something? And as a designer, you have to have a very good answer for this to this question. Now, what happens if it's minor damage, like, okay, you hit a piece of wood, it's no problem structurally, but it really upsets the hydrodynamics. And minor damage is usually the main one, where you hit something, a floating drum or a crate in the water or something, damages to the leading edge. but you also have to have an answer to what happens if you do hit a rock or you ground the vessel at speed. So there's very little in terms of design information. What are the design loads when you hit something at speed? If you hit a floating log in the water, what is the actual design load? There is only some limited information from US Navy research back in the 1960s, which sort of give you a way forward. But also now with the development of carbon hydrofoils and hydrofoils on high-speed sailing ships, this idea of designing hydrofoils to withstand impacts with floating objects, I think is something I would really like to see and actually get involved in to better improve or to improve the hydrofoil designs. For example, here is one of our boats, which it's an 11-meter Hyzercat, which hit rocks, these loose rocks at a high tide at 30 knots. And you can see how the hydrofoil sort of bulldozed and pushed the rocks forward. And fortunately, the hydrofoil didn't really get damaged, only very minor damage, and it could go back into service. But in terms of, so basically we know our hydrofoils are strong enough, the bolting connections are strong enough, but ideally what you want is a system where, yes, the hydrofoils do not get damaged when you hit in this kind of condition. But if it had to be something harder and more solid, you want the bolts to break off and shear off without damaging the hull. So it's a very sort of complicated sort of mechanical engineering problem, and partially hydrodynamic, I suppose. But it is an area of research which would be very interesting to pick up. The last papers I could find on this subject were papers published in like 1965. And so really we fabricate our hydrofoils from stainless steel, sometimes in titanium, but it is 3 times the cost if they are done in titanium. Or for very small craft, aluminium can work as well. The modern development is really in composite materials and to make the hydrofoils lighter, also to solve the galvanic corrosion problem. Stainless steel hydrofoils on an aluminium ship is also always a little bit more complicated for preventing corrosion. And so we are now venturing into this, looking at composite foils together with some specialists. Right now we're working with a company, working with a company in Austria to develop these foils. And I think there is a big potential, but again, only if the problem of hydrofoil impacts with floating debris can be solved. Because if you damage the leading edge of a composite foil, typically the water pressure will sort of delaminate the whole foil. So I will finish off with one more slide just to show you. At the moment, we are working very closely with a company called CTech in Nizhny Novgorod. They are our sort of design partners in Russia. And we are now developing this vessel and variants of this vessel as a hydrofoil supported catamarans. And it looks like we have a Russian state-funded project. And hopefully within 18 months or so, there'll be one of these vessels running on Lake Baikal. And it will be the first Hyzercat hydrofoil supported catamaran running in Russia. So I'm very positive for that, and looking forward to that project sort of materializing. So that is really, I see I'm on to 30 minutes, so I think that's where I can stop and take any questions that anybody may have.
Yes, thank you for your interesting presentation. Is there any questions, dear colleagues?
Yes.
Yes, Nikolai Kornev. You can turn on the microphone.
Sorry, the microphone is muted.
Nikita Traskin.
So my question was, you are talking about combination of simple technique, simple approaches, such as Savitsky, who has developed, as you remember, for prismatic hulls of seaplanes, and
Yes.
Kornev's outer wing, which deals mostly, if I remember well, with wings. So when you do these
hulls,
approximations, yes, which are certainly very constructive, and of course, probably are the best way to have the first iteration, do you treat them independently, the hull and the foil?
With the simple methods, when we are using simple hydrofoil theory and planing theory of Savitsky, those were combined into a single system where we calculate the equilibrium condition, running condition of the boat, and we have simple corrections for hull foil interactions. And it's approximate, but with experience and incorporating sea trial data, it is often good enough to get the main foil design worked out. And what we also do with our foil designs is we're building some adjustability into it, because more often than not, once the boat is built, there are changes in weight or changes in center of gravity, and you anyway need to have a way to do some final adjustments. If we're using auto wing, or then generally I'm looking at the foil system alone, and because it is not so easy to combine the two together. And so we will either look at the foil system alone, the hull alone, and then combine those two separate results and make some empirical corrections for any interactions which we think might be there. Yes.
One more question about fuel consumption. You said that for those who are customers, it is not very important, but I understand as you fight with motions of catamarans, which is a problem usually for catamarans. And,
yes.
So when you do it using wings, which is a very reasonable way to do, because wing damping systems have been accepted in displacement shipbuilding. Yes, of course, for decreasing motions. So
yes.
Calculations for ships with wings show that when you decrease motions, you also decrease fuel consumption.
Yes, that is true.
Because I understand that when you use wings, you usually decrease the added wave resistance.
Yes,
and
that's
that
correct.
is, you decrease the power required to move at a certain given speed. Yes.
Yes.
So, I mean, did you compare, for example, you're talking about wings fitted under the keel or within the hulls, yes, that is between the deck and the keel, and how does it compare in terms of fuel consumption? I mean, just
in general terms, yeah. And generally the more you can lift the hull out of the water, the better for the fuel consumption. Like the lift to drag ratio, of the hull is typically around 6 or 7, and while of the hydrofoils we are, often in the areas of like 20 or in the best cases maybe 25. So the more weight you can carry on the foils instead of the hull, the better you can reduce the fuel consumption. But there's always a compromise. So if once the hydrofoils get very close to the free surface, then, and the hull is very far out of the water, your stability starts to be a problem.
It's questionable. Sure.
Yeah, so because the hull is actually provides quite a large part of the stability, because the slight changes in the draft or have very big effects on the load, on the hull load, or how much weight it's carrying. So the hulls dampen out motions very nicely. But if you lift the hull very high out and you have a shallowly submerged hydrofoil, the biggest problem we face is usually in a wave that hydrofoil pierces through the surface, ventilates, and loses all its lift. So then the vessel basically drops off the foil, and then it starts to rise up again, drops off the foil. And you get a kind of a very slow porpoising kind of motion. And so you can't go too far in any one direction. You have to find a reasonable balance between stability. It's also a seakeeping problem at the same time. But generally, if the seakeeping or the sea conditions are not too rough, we try and lift as much hull out of the water as is practical for that particular application.
Just final small question. You showed this was called Linda, I think, MTD.
Yes, Linda Express, yes, that's right.
They were using interceptors, or as we sometimes call them, spoilers. Do you introduce spoilers into your designs or in your calculations?
Yes, that's a very, very good question, actually, because we've recently started looking more and more into that. And what we have established, again, Professor Kornev supplied me with some Russian papers many years ago on calculating interceptors. And what we found is that the efficiency or lift to drag ratio of the interceptor is really good if the height of the spoiler or interceptor is low. So if you have a large span at small height, you can get a lift to drag ratio of that interceptor, which is almost the same as a hydrofoil. So, and because you get many commercial interceptors on the market, which are adjustable, they are almost plug and play systems, we find that fitting that instead of a rear hydrofoil does make good sense. It is you get the lift and trim control. You do not lose any efficiency, and it's a well worked out system. Also, less cost for the owner. So yes, we are using them quite extensively now.
Thank you very much.
Thank you.
Well, Nikolai Kornev, it's your question now. You should turn on the microphone. Mr. Kornev.
Your microphone.
Yeah. Okay, I have some short questions. The first question is, what about washing? If you would like to put into operation on Baikal Sea, this, of course, washing problem could be very important. If you compare washing of this Hyzercat with conventional catamarans.
Yes, we've done some calculations on, had some measurements of wash in the Washington state in the US, especially, let me find the vessel quickly. Basically, this vessel was tested with and without hydrofoils, and the wash was measured. And we found that sorry, my children are outside. We're all working from home. So sorry, they don't have a mute button, so excuse the noise. We found that the wash energy and the wave amplitude were both reduced by 30 to 50%.
Okay.
So it is yeah, the hydrofoils are a benefit there. And this is for a system which was not really designed for wash reduction. If you are using sort of wave cancellation between front and rear hydrofoils, I believe you can improve that further.
Okay, thank you very much. So you mentioned also the program from SimTef to calculate, I think, wave loadings.
Yes,
ship, I don't know, ship
X varies, yes.
Yeah, and this is strip method. It means
It's
you use it just for slender bodies, for slender hulls, but you have also wing. How to calculate if wave loadings on the wing, because strip theory is actually applicable for the any ships with slender hulls.
Yes, this is a high-speed strip method. I think it is based on the work of Zhao and
okay, yeah.
yeah. And what they've done is they've just added a reasonably simple method. You a lift curve slope for the hydrofoil into the method. So as the vessel moves, it will calculate the forces from the hydrofoil. So it is relatively simple, but we found it gives reasonable results as long as the hydrofoils are not ventilated. Then of course it is, the correlation is no longer good.
And last question. So you mentioned many times ride control for such ships.
Yes.
So if you mentioned also Linda Express, and they used their wing which was moving. Yeah.
Yes, they had a wing which was where is it? Okay, yeah, they had the whole wing could rotate. The front wings were on hinge pins, so you could change the incidence angle of the foil.
My question is, thank you. My question is, some of control systems, they use so-called prediction of sea state. It means what is the principle of this system? They detect waves in front of the ship, maybe 100 meter in front of the ship at the distance of 100 meters, and they generate some control signal to overcome this perturbation. Yes. Will come maybe in 1 second. So do you know about the application of, for conventional ships it was done. For the fast ship, has anybody done it or not?
To my knowledge, nobody has done it very successfully, sort of predicting the waves ahead of the ship. And in all our projects, we've never sort of come across that firstly, the clients really want to go into that level of expense for the larger ferries, yes, but for the smaller vessels, generally they will opt for much simpler systems. And I have not seen, I've not followed that development very closely, basically because there's been no demand from our clients for that up to now. So, but to my knowledge, no, it has not been successfully implemented yet.
Okay, thank you very much, Gunther. So is it, I think, your second presentation at the State Marine Technical University in St. Petersburg?
Yes.
Yeah, the first one was in 1999, if I remember correctly. Yeah?
About then, yes.
And we see,
I hope to be in St. Petersburg this year, so I would very much like to come and make a visit again at that time.
Yeah,
when I get there.
So I would like to say we see real progress, yes, within last 20 years, both in technology and second also in development of methodology. I mean, run simulation, then last samples with collision samples. So then, thank you very much. Yeah, this is
Thank
all.
you.
Right.
Well,
Thank you very much.
Nikita Traskin, it's your question now.
Good day. My name is Nikita Traskin. Actually, I had the same question that Professor Nikolai has just asked to you. It's about Tip Vortex.
Yes.
I wasn't familiar with this application and what are the advantages of using this software. So,
Okay.
but after he asked you, so it should be strip theory here.
It is a high-speed strip theory. You see, as a practical design tool, it is not it's not bad, but there is definitely opportunity for more for a better tool, because the hydrofoils are, the one problem with it is it doesn't really take the lift curve slope is input in a very simple way. So if the foils become very shallow and the lift curve slope becomes flatter for the hydrofoil, then it's not working that well. So one has to make quite a few assumptions to get good answers, or make some good guess values for. So I don't think the only advantage of it really is it's fast. Within one day we can analyze very many different foil configurations and find a suitable, the most suitable one. But I think eventually this work has to be done within a more complex CFD method to get proper results.
So you haven't tried to choose the best one here and put it in a CFD to make a CFD, sea-keeping CFD?
No, actually this project here, which I'm showing on this slide, this HFlex project, is in progress, and that is really the next step of this, to see, is to do a sea-keeping analysis in unsteady, really unsteady conditions, irregular waves, and see how it compares, especially for these conditions where the foil starts to ventilate.
Okay,
And
thank you.
I'm hoping to publish that in a paper, so maybe by the end of the year would be.
Thank you.
Thank you.
Well, dear colleagues, are there any more questions?
My question was about this work. Was it Zhao and Faltinson?
That's the one, yes.
Yes. Okay.
John Faltinson, that's the theory, yes.
Yes. Gunther, when are you coming to St. Petersburg? More exactly, can you tell me?
Probably end of June. I hope just before your summer holidays. No.
Okay. Let us know, please, because
Okay.
I'd really very much like to meet you.
Thank you. I will definitely keep you posted.
Well, any more questions? Well, in case there are no more questions, please look at the chat. I posted a link to our YouTube channel where we publish these presentations and discussions. Well, thank you very much, Dr. Gunther.
Thank you very much.
It was
It's
very
my
interesting
pleasure.
presentation. Yes, it's pleasure is all mine, or all ours. We really hope you will come to our university, maybe make a live presentation here.
Thank you.
Well,
I would very much like to do that, and hopefully we can explore future areas of research or cooperation. It would be interesting. Thank you very much.
thank you. Well, so I think we can finish this now. Thank you very much. It was really a very interesting experience. Actually,
Okay.
I think it was our first experience of such a seminar in English. Yes, for me,
Okay.
it was really a first experience. Well, thank you.